James from JTAG Technologies. I work at the UK sales office of our company, which is actually a Dutch company based in Eindhoven in the Netherlands. Just going to cover a few topics today, give you a little bit of history to JTAG and how it came about, a technical description of how it looks at a device level, and then we'll move on to test possibilities at the board level, what you can actually achieve with JTAG if you have it implemented on your design. And then finally, just a few slides on how often it's added into ATE systems, how best you can add it into an ATE and so forth. And then obviously if anybody's got any questions at the end, that'll be fine too. The history of boundary scan, it really came about in the early mid-80s when the first surface mount devices were being developed and manufactured, and traditional test methods using bed of nails testers were no longer able to satisfy the access requirements for testing the devices and the circuit boards themselves. So in-circuit test became less and less tenable for these new designs, and so a group of engineers formed what was called the JTAG committee, the Joint European Test Action Group. So if people didn't know that, that's where it started. And within a year, though, they dropped the E and it became the JTAG group when we got some American involvement. And over a very relatively short period of 4 or 5 years, they put together this built-in test standard, which got an IEEE standard reference 1149, and known as the Test Access Port and Boundary Scan Architecture. So from its very inception, it was actually a tester interface, and not, as some people believe, a debugger interface, but which it became useful for later on. Other standards have followed since. So we had, effectively a defunct standard now, 1149.4, which was an attempt to add analog testing into the boundary scan area, and then a unified standard for in-system programming of devices, IEEE 1532, an adjunct called ACX test, also known as 1149.6 for testing low voltage differential signals that could be AC coupled. And then there's been other attempts to add to the standard using BIST functions and so on. But we'll just look at the basic stuff today. And really this slide just illustrates what happened over a rapid period of years in the 90s, when we went from predominantly through-hole components that were easily tested with conventional in-circuit and manufacturing defects analyzers through to the more surface mount devices which we see today. And here we can see some of the challenges that those surface mount devices presented. So, for example, is this a laser pointer here, by the way? This little thing there? No, it doesn't do that. Okay, never mind. What you can see there is when we start to use more surface mount devices and higher density circuit assemblies, we end up with buried vias, blind vias, and buried tracks that you can't necessarily access with conventional test methods using in-circuit test pins. So by being able to access the pins or balls of the device via the internal logic wafer from the wafer itself, through the bond wire, through the ball, and then along through the tracks, you can test more of those hidden parts of the board. And it also gives the ability to test things like bond wires and other cracked balls and things like that, which you wouldn't be able to do with an in-circuit tester or a flying probe tester, for example. How does it work? Well, any device that supports JTAG boundary scan is equipped with a block of logic called the Test Access Port, or the Test Access Port Controller. That is fed by a bunch of signals here that you can see. One, test data in, test data out, two fundamental signals there, test mode select, test clock, and an optional logic reset, TRST. In addition to that, we have a set of registers. So we have a bypass register, which allows you to bypass the device and exclude it from any test activity, and it will resume its normal operating mode. There's an identity code register, which you can read out, which gives you a manufacturer's code, a device code, and a device revision number. Then there's a thing called the instruction register, which can process a small set of instructions. There aren't very many instructions required for a device to be boundary scan compliant. So that's X-test, bypass, sample preload, and optionally identity. And then the fundamental register that we use for most of the testing, which is this boundary scan register here. So the boundary scan register are these little circles that are shown on the diagram, and they represent a bunch of flip-flops and multiplexers essentially that can capture data on input pins and propagate data onto output pins. And in some cases you have multiple cells per pin. In the case of an I/O pin on an FPGA, for example, you might end up with 3 scan cells, an input cell, an output cell, and an output control cell. And they're all linked together to form this boundary register, as I say, which is operated on using the X-test mode, external test. Additionally, we have some devices will have private instructions which might relate to programming of devices. So, for example, FPGAs and CPLDs will have a bunch of extra instructions over and above the standard ones to allow the device to be configured and programmed and so on. Or there might be some BIST instructions or other types there that are specific to the vendor. Now, the full set of information about a device and its boundary scan capability is encapsulated in a model file called the BSDL model, Boundary Scan Description Language Model, which is like a subset of VHDL that just describing the boundary scan capability of the chip. And if the device manufacturer claims to be compliant to this standard, 1149.1, then it's incumbent on them to provide this file for download. Okay, so that's how it looks at a device level. What we want to do now is what you can do with it, which is the important thing, I guess. So if you imagine you have a design with a couple of boundary scan compliant parts on it, first of all, let's say an FPGA and a microcontroller or microprocessor. It's quite a common arrangement these days. Then obviously one of the first things you want to do, go back one, is test the scan path infrastructure. So that's testing you've got continuity on the TDI, TDO, TDI, TDO lines. Back to the tester, because without continuity there, you no point in really going any further. You have to debug that part of the process first before you can step on to more tests. But following that test, you can use the boundary scan register here, for example, to clock data patterns from device FPGA through to device microcontroller. You can set buffer enables and output enables to allow the transition of data between the two devices, and you can declare resistors such as those series resistors as transparent, and that allows you to do quite a lot of connectivity testing. And the way the software works is it only uses quite a small number of patterns, so that the test is pretty rapid, and the diagnostics is also quite accurate, and it will identify shorted connections, open pins, stuck at 0, stuck at 1s, and so on. So it's a good way of testing quite a large part of the board using the interconnections test. Over and above that, if you've got things like LEDs and things like that, you just want to blink LEDs and do some visual testing, then that's an easy thing to add, because the boundary scan can access those nets and light them up. Similarly, switches. If you add some digital I/O external to the board, then you can also extend the testing not just from boundary scan device to boundary scan device, but also boundary scan device through edge connector. So your digital I/O module is itself containing more boundary scan elements, could be FPGAs, for example, and you can include those as part of the interconnections test, or you can make a dedicated test up to those connector points. So it's extending the test capability to those things. You're fooling the system really into thinking that the edge connector is itself more another boundary scan part. Pull-ups and pull-down resistors can be tested. You just drive the value to the opposite. You drive the net to the opposite value, and then tri-state the driver, and then capture the value that it's swung back to. So that's a fairly easy thing to add. Memory interface tests. So from the boundary scan register, you can simulate memory writes and memory reads. Just send a handful of writes and reads to the device to check again for the integrity of the address and the data lines. So it's not an exhaustive write to every location search, but it's a careful choice of patterns to allow us to determine any shorts or opens on those lines. And we support up to DDR4 memory as well with this, by the way. So it's quite it's quite up to date in that respect. As I mentioned before, if you have a device that is compliant to the adjunct standard 1149.6, then we'll have an extra instruction, ACX test, which allows you to apply a high-speed pulse. This should really be shown as capacitively coupled here maybe, and you can apply a high-speed pulse that will be recovered at the other side of the capacitor at the receiving end, and again that will allow you to detect any opens or shorts on those low voltage differential signals. Commonly in today's sort of industrial designs, we see a lot of I2C and SPI bus parts. They're quite easy to test. We've got automated tests that will just read back their identity registers just as a quick look-see, I'm here. But we've also got some capability to write Python scripts that allow us to do some more in-depth testing on those parts. So if you want to set up real-time clocks with a time, program them with a time, or if you want to read temperature sensors or read ADC values or things like that, then we can do that quite easily also. What else we got here? Analog I/O. Some of our controllers have analog I/O capability as well, so we can apply an analog voltage or measure an analog voltage via the boundary scan hardware that we supply. And as I mentioned, functional testing of logic blocks using some Python scripts. So if you've got more exacting testing you want to do, you have to do a lot of register writes and reads to set up a device. Then and there's conditional branching involved within the test script. Then, as I say, we've got this Python development environment that's very useful for applying to that type of situation. Finally, I think I must have skipped a slide there. So we've got what we call some emulative test capabilities. So in the microprocessor scenario here, you will find typically there will be a core, a RISC core, for example, from ARM, or something Coldfire, or NXP, or Freescale type core microprocessor system. And these cores are often accessed via the JTAG interface also. And to support that capability, we have a set of modules called Core Commander. They're applicable normally to a specific core family, like ARM Cortex-A or Cortex-R, for example. And that allows us, from our JTAG tools, from our Python scripting tools, in fact, to perform memory writes and memory reads from within the device. So we're writing from the core to memory spaces to set up registers for particular access to certain IP blocks within the device. So that could be A to D converter, for example, which is internal to the device. It could be, don't know what that's supposed to represent there, but embedded memory controller, EMC, sorry. Embedded memory controller. So rather than using the boundary scan register to perform the memory interface test, you can run it at speed using the embedded memory controller, and so forth. And the same thing applies over here on the FPGA. We have a translator block that allows us to bridge from IEEE 1149 into an embedded interface such as Core Connect, Wishbone, or some other type of arrangement like that. So it kind of extends it from the basic traditional boundary scan into something a little bit more powerful, in fact. And it also adds this sort of capabilities for analog measuring and so forth. Okay, and here's a summary of some of the manufacturers we support with their cores. So I got a little bit stuck at that point because I couldn't think beyond the ARM because they're so prevalent these days. But we also have support for the DSP cores from analog devices, microchip PIC, and PIC DSP, I think it is, DSP PIC, TIC 2000 core, and so on. All right, just pause for a second now because we're just going to look at automatic test equipment, and I'm just going to start with a few sort of summary slides on why we test in actual fact, because not everybody does, believe it or not. Some people just build things and hope and keep their fingers crossed. But really, the message we're trying to get across to people is, if it hasn't been tested, then it doesn't work, and that should be the assumption, right? You don't build an aerospace product and put it in a plane and think, well, it should be all right. You have to make that assumption that it doesn't work. So and of course, assumption that it does work is the parent of all foul ups, mess ups, whatever up you want to put in there. And tests can vary, of course. So if you look at possibly the most simple electrical product that you can buy, would be something like this, a torch, and a simplest functional test would be to turn it on, and does it light up? Right, that's it. That is your functional test. And some people are still providing functional test systems that do that. So power it on, does it light up? Great, ship it. Well, that's fine until it doesn't light up, and then you've got, want to find out why. So the whole key to testing is to divide and conquer the assembly and test as much down to the lowest possible component level you can. And in the case of this torch, for example, you would add some probes in order to test the actual switch itself for continuity. You test the voltage of the individual cells, you test the bulb for continuity, and so on. And with each added probe point, you're increasing your diagnostic resolution and giving you a more targeted diagnostic. And that's really one of the key things you need to bear in mind when you're building a test solution for anything, really, using boundary scan or using any other technique. So one of the tools that we have in our software system is a fault coverage examiner, and that can give you a clue onto how much fault coverage you have actually got and how targeted your tests are, and it will indicate a test coverage on an individual net basis. So it will say that a net is 50%, 75% or 100% tested, depending on how many nodes of that net it can exercise, using boundary scan or using I/O access or what have you. Okay, so that gives you a good flavor, and we can overlay that data onto schematics and layout diagrams in order to give you a visual overview of the test coverage. And of course, you've got these statistical outputs as well available. But overall, what we're trying to do here is test these types of failures. So manufacturing failures that you would typically see. Tombstone resistors, solder shorts, bad reflow of your ball grid array parts, and so on. And that's really where we're heading for here in our ATE. Now, we saw all those test possibilities earlier on the diagram, what you can achieve with boundary scan, your interconnect test, your infrastructure test, your memory tests, your I2C device tests, and so on. How are those generated? Well, we have two options available to you. You have automatic program generation, where the test system imports the CAD data, the netlist information, if you like, from your schematic entry system. It imports models for all the devices, so that's BSDL models, the boundary scan models for the boundary scan part, and models from our extensive model library for the non-boundary scan elements, the memories and the bus logic and the resistor packs and all those other things. They're all processed, and typically it's a button pushing exercise to get a list of tests produced for you from that CAD package and that model package. Alternatively, if you want to do something a little bit more exacting, you can use the scripting system that I've mentioned, where you can group pins together and assign a group of pins to a variable and pass that variable using different functions to write a value or read a value. There's also a high-level I2C and SPI bus library, so make it easier to access those types of components also. Here's a flow diagram for the automatic program generation. So as I say, you've got your CAD data from your schematic entry system, whatever that might be. You have your BSDL models coming from the IC vendor's website, or you've got your non-boundary scan cluster models, as we call them, supplied within our Provision package. That all gets fed into the tool. There is a model mapping process where you obviously have to map the instance name from the schematic system to the actual model itself. But once that's in place, automatic program generation takes over, and we get this list of test capabilities here. The alternative method, as we mentioned, Python script, where you can declare, for example, we've got on one of a very, very simple test is just to set a walking one pattern across a lead bar that we have on our demo board. So in order to do that, you can declare a group, declare a variable if you like, we call it blue LEDs, and then we assign all the pins of the boundary scan device that we want to control in order to light those LEDs to this variable, blue LEDs. And then in this for loop here, we just say for I in range, start 0, increment 8 times. That's how Python works. Drive blue LEDs, 2 to the power, loop counter. That gives us our walking pattern, and 1 second to view the LED, and it just loops round and see. So a very simple, compact system for making quite a powerful test. To apply the tests, you need some hardware. That can come in the form of an embedded controller that you can build into a fixture system, a test. This is the ATE part now, I guess, and we've got one of these on our stand, so this is built into a bed of nails fixture. This particular module has 2 test access ports. It has a bunch of digital I/O on it as well, and also some analog I/O for measuring plus or minus 16 volts or single-ended up to 30 volts. Has some frequency measurement channels as well. So it's kind of almost like a mini tester built onto a very small board. And if you build a cassette-based fixture, you can build personality adapters for each different board that you're testing. So you can use the same resource hardware, power supplies, boundary scan controller, and so on, but direct the test signals up to different test points. There's a benchtop version that looks like that. We've also got one of those there. Okay, so where would you expect to find this type of hardware? Well, as I say, we've got that one's on the stand just around the corner, so you can come and look at that if you wish. So we're building in a power supply and the basic boundary scan hardware into a little tester. We have also other variants of our tester hardware, faster ones with more test access ports, and ones in different form factors. So we have PXIe and Ethernet controllers as well. So if you're building a PXI based test system, and this is from one of our partner companies, ATE Solutions, then it fits into there quite nicely. And then we also have relationships with other tester vendors. So here, for example, is a picture of an in-circuit tester from Speyer Electronics, and we have a relationship where we can build our tester hardware into their third-party systems. Software choice. Obviously, if you're building your own test system, what software are you going to choose to run it and execute the tests, analyze the results, and so on? We have quite a number of choices here as well. So once the tests have been developed, either via the automatic process or via the scripting process, how do you want to apply them in the actual factory environment? Well, is there an in-house standard? Because quite often people will have their own preferred format or framework for running tests, so that might be a consideration. What skills are available to run it? You know, if you're using something like .NET framework, then you need quite skilled programmers to be able to utilize that software system. If you're looking at more hardware engineering types, then perhaps something as simpler like the Python scripting is a better choice, and so on. So, also, what specification have you been given? So, as a supplier of test services as well as test equipment, we really encourage people to supply us with accurate test specifications, because sometimes we just give them a board and you say, well, what, just do what you can. Well, how long is a piece of string? Test as much as you can of the board. Well, that could take years. I mean, we could write a test for every minute little register locate or whatever. I mean, there's got to be a cut-off point, and we need, it's very, very helpful to have a proper test specification to work from. That's one of the joys of this system. So just finally, to wrap up, some of the key software or the main software environments that we come across, as I mentioned, time and again here, Python, not only to construct the individual boundary scan tests, but also as a wrapper program to execute them, and also to call other test equipment elements. So, for example, within the Python library, free libraries, there's a thing called PyVisa, Virtual Instruments Standards Association control for other test equipment. So you can use the Python to control oscilloscopes or DMMs or other types of hardware, and tie that in together with your boundary scan. So if you were testing a board with a D2A converter on it, for example, you can use the boundary scan to stimulate the digital to analog converter, and use a DMM from a third-party vendor under the control of PyVisa to take the measurement, or use the PyVisa to control a power supply to ramp up the power supplies and that kind of thing. So using the two things in combination, you can create quite a powerful test environment. A lot of people will be familiar probably with National Instruments products, LabVIEW, Test Stand, and so on. And we have some off-the-shelf drivers so that you can execute the automatic generated tests, and actually also create the scripted tests. So for each Python routine that says set a value onto the variables that you've declared, there's also a LabVIEW VI for doing that same thing. So that's another powerful solution for those people who like the graphical programming environment rather than the traditional typed code.